Welcome. In today's OTT, we're going to explore some Lambda tuning. I came across this tool on GitHub, and I find it quite interesting because it's something that you can deploy to your AWS account. So it's fully self-hosted, and by doing that, you have access to this state machine, which is a step function that takes in a couple parameters. And as a result, it's going to test the Lambda function that you pass with different memory sizes and output a chart of execution time and also cost. So I find it very interesting. It has some cool use cases where you can see based on the input size that you put to your Lambda, how is time and cost going to be impacted. And I think it's good to design for these situations because, well, you're going to see in the results, you can often increase memory, but reduce the cost because it's more efficient. So less time for a Lambda executing results in less cost as well. And another interesting fact is that with Lambda, you don't control virtual CPU directly. So you can only tweak memory. And as a result, it's going to change, it's going to impact a little bit the virtual CPUs. And online, I found some articles, and the way they usually show is it's not guaranteed, but there's a certain correlation between memory and CPUs. So the maximum that I was able to test was around 3 megabytes here, and it's going to give you 2 CPUs. But yeah, let's take a look at so let me show you the setup. First of all, we're going to be testing a Lambda function that is CPU and memory consuming, because it's also not going to be very helpful if the performance of your Lambda is bound to network, for example, and you increase memory and CPU, it's not guaranteed to give any difference. But if you have a Lambda that is doing data processing in a way, you're going to see a lot of difference. So what I have here is this project. It's getting deployed with SAM. It has one Lambda to calculate a score, and it's using a Lambda layer. And in this layer, we basically have some data, and the data is different data sets. So a data set with 1,000 items, 10,000, 30,000, 60,000 items. And we're going to see how the Lambda perform at each memory size processing this data. It's a Go script that is performing this calculation. So we have a little bit of concurrency and parallelization going on with Go routines. And there's also some interesting findings as like what's the impact of parallelizing versus not in Lambda. Yeah, so let me show you here the Excel sheet. So in this Excel sheet, I have the results, and we're going to be looking at charts. So let's start with a very small input size. So let's say our Lambda is only processing a file that is not even 1 kilobyte, and it's only 50 lines. The result is that it doesn't matter the memory. It's pretty much constant time because it's so little data that you're better off choosing the smallest amount of our test, so 256 megabytes of memory, and that is going to give you good results. And if you increase memory, you don't get any improvement in price. And things start to change if we change the input size. So we jump 20 times, we go to 1,000, and at 1,000, the chart changes a lot. Now, 256 gives you a much worse performance. So it jumps up the time that it takes to process. And we're going to find the cheapest to be around 1024 megabytes. That's going to be the cheapest. And also, as you can see, in terms of Lambda execution time, it fell down a lot. But after that, we get diminishing returns. So the Lambda starts to cost more, and the time it takes to execute remains constant. So it really doesn't make sense for this input size to continue increasing memory and CPUs, since we're just going to be paying more and not gaining any performance increase. Then if we 10x from there, we also see some different. Now the line is a lot more flat. We're going to find the best deal at around 1,500 megabytes over here. It gives us a good performance, and performance continues to go down after, but not enough to justify the cost, because the cost starts to go up again. And we're going to see that if we start increasing again, now, if we triple or double the input size here, we're already at a stage where we're getting diminishing returns. So for both 30,000 and 60,000, the cost remains kind of flat. And the decision is basically around performance. So it definitely doesn't make sense to pay the same amount, take 10 times the time to process if we can reduce the cost and improve a lot the performance. And there are a couple caveats to this testing as well. My AWS account only allow me to have up to 3008 megabytes allocated to a certain Lambda. So I could not explore these numbers over here of 3 and 4 CPUs. I'm pretty sure that would change the results, because I ran this locally. And if you can see here, this is me running locally, and the results are much more consistent. You can see that if I set the Go max procs, which tells Go how many threads, OS threads it can use. If I specify to 1, it has a worse time, 17 seconds. But as we change to 2, 4, the time goes down. So at around 4, we're getting 8 seconds. So that's twice the performance by adjusting this number. And so on Lambda, I think we would see a similar result. And we also have diminishing returns testing this locally. S4 and 8 cores doesn't change the result. It remains around 8 seconds. So we're good at 4. But yeah, in Lambda, you have to consider cost and volume and input size. So I think it's pretty useful to find some time to do these testings and set up an environment like this where you can test different input sizes and you can deploy this power tuning to your account and see results. And I think one last caveat that I would share with you, let's do a run together just so you can see what it looks like. This is my function. These are the different power values we can use. This number right here, the higher you set, the better the data, because it's going to execute more times. So the data is going to be more rounded, but there's a caveat, and let me show you. My account initially only had a 10 of unreserved account concurrency, and AWS sets that number very low. I'm pretty sure for safety, because if you have, so AWS has a limit of 1,000 concurrent executions in your account. So they want to make sure that you don't hit that limit. So every single Lambda can only go up to 10 by default concurrent executions, and they start to throttle after that. So if you want one specific Lambda to have more concurrent executions, which is a common scenario, you have to open a ticket in AWS support so they increase your service quota. So I did that, and it took less than a day, and they increased it to me to one And well, this is unreserved, but I can also reserve. So right now, the risk that I have by having requested a ticket is that if we round up, it takes only 7 lambdas in my account to reach the throttle limit. So if I have an API, lots of lambdas, and 7 of them start to throttle, all my lambdas are going to be throttled. And that's another thing why it's super important to have separate accounts per environment. Because if you're going to do a load test in QA, let's say, you definitely don't want that to halt production and affect your real customers. So having a separate account makes sure that you don't cross the limits of the environments. And yeah, increasing this value makes it easier for me to hit that limit. And then also eventually, if 1,000 is not enough for you, you can also request to have more concurrency in your entire account. That's definitely worth doing for production. Yeah, so let's run this thing and see what happens. If you never used the state machines, it's pretty neat. It gives you this visual and it's going to initialize you. This one comes for already. You can just go over here and then deploy. You can deploy it with SIM. You can deploy with CDK or even the IUI. You just click deploy and deploys to your account. As long as you have the enough VM permissions, it works. So right now it's running. You can see it's going pretty quick, which shows the 10,000 payload. And you can see the lambdas with more resources already finished, and the ones that are less memory abundant, they are still in progress. So once they all finish, we're going to get a, you see, now it's running the cleaner, and pretty quickly it went to the optimizer. So if you go over at the end, you can copy this visualization. If you go into that link, it gives you the visualization. So yeah, that's pretty much it. You can, through this UI, you can also compare. So if I take the previous run that I did and compare with this run that we just did, we can compare now with before and do more like data analysis. You can see a couple of things fluctuate in terms of cost, like a very tiny change in time changes the cost because it's very, very low, but still it trends in the same direction. So that's pretty much what I wanted to show you. I think it's an interesting tool. It's worth looking into it. You can also play around with the strategy. I think it makes sense to go with the default, which is to optimize for cost, but you can also optimize for time and also a balanced. So if cost is not your biggest concern, you can optimize for half cost, half time, and get the best deal. Yeah, that's pretty much it. Any questions, comments?
Looks great, pretty interesting. So
I have a question. Well, great talk, Marcelo. Really interesting, this topic. I just want to know if we want to test with real cases, like clients, what do we need to know? We need to know how much data each Lambda is processing to start playing around with this fine tuning, right? Or what is the kind of how we can test it?
Yeah, so let's see. In terms of getting this ready to test, you go into the GitHub, you follow the deploy instructions, and you're going to have a similar setup that I have here. Then you're going to copy the ARN that you want to test. So you decide which function, let's say it's CPU intensive or memory intensive. So you want to run a couple tests. You're going to paste it here, and you might have to do adjustments, right? Because if the Lambda depends on database data or S3 data, you have to make sure that the data is there. What I did here in my setup, I isolated the data issue. Basically, I put a bunch of data sets into a Lambda layer, and I read from the file system to make sure that I'm only testing the processing of the Lambda and not network and other things that might fluctuate. So I think you could do a setup similar to this, And in terms of testing to customer, it's important to understand what's their usual utilization. So, for example, in my application, it might be that we're always dealing with only 50 data points. So this is the one that is most important to benchmark against. And if you, let's say, want to optimize cost, and the client says, hey, how can we reduce our billing? You could think of a batching strategy. So the Lambda, instead of getting only 50, it could get batches of 50. So one execution could process more data. And then for sure, you're going to have to adapt the memory of the Lambda. But since you don't know, you can use this tool to test multiple memory sizes, and it's going to tell you which one is faster and cheaper for the data that you're using. Does that make sense?
Yeah, thank you for the explanation.
And Marcelo, regarding this tool is to fine-tune the configuration of Lambda, so we can have like a balance between cost and execution time or performance. And then you talk about your Go Lambda, and then you mentioned the parallelization feature. But I miss here, with Go, what you did is to split the work into multiple threads and improve the computation time. And that thing, it's an aggregation over this layer. You are saying like, I didn't understand here that where's the place of Go within this scope.
Yeah, so about the use case for Go, this is basically a script that is an exercise. So each data set was generated using this cellular automata. So it generates a bunch of patterns. And the goal of the Go script, what it's doing, is finding patterns and computing a final score. So there's some logic and rules about like how each line in the file represents a position, and then positions that are neighbors to each other, they are going to form groups and they're going to score. And so it's a deterministic script in which the same input always results in the same output, and also the order in which they appear should not change the output. So as you can see, I have some data sets that are shuffled, which means I took the lines and I shuffled them around to make sure that the score would remain the same. So as far as I tested, the algorithm is correct in terms of execution. And in the way that it was coded, it's correct with a single thread. And it also supports multi-threading, because as I increase the number of cores, Golang concurrency allows me to run things in parallel and without affecting the correctness of the program, which is super important, right? You want to increase performance, but you cannot lose correctness. And the way that I do is because this is not a super, how can I say, complex situation of concurrency, in the sense that
I think the question that I want to do is related to cost, because once you put in place Go, you can then increase the threading, let's say the cores, and you will have like a sooner response. But as well, it's a kind of trade-off, because you increase the cores, but you reduce the computation time. But at the end, what would you prefer? I mean, it's a matter of the client or the situation. What do you prefer, to have the result sooner and pay for more cores, or to pay less and wait more, right? It's a matter of the use situation.
It's a matter of the use, and it's a lot matter of the algorithm. So if it's a program that supports and does concurrency very well, it's worth batching them. Let me show you here. So as you can see, as I increase the number of the batch, the price was pretty much flat and even reduced. And here the 60,000 case, this input is 700 kilobytes, and I got the best price at around 2000 megabytes of memory. So that tells me that the concurrency is being well used, because at this point we're getting 2 cores out of the Lambda. As per this table, at around 2000 we get 2 cores. So it's using well those 2 cores, and it's using well enough the memory size that it has. But if we start increasing memory, the price starts to go up. And I think we're going to see this trend all over until, for example, we reach 4,000 or 5 or I guess 6,000, where we have 4 cores. I think that's where we will reduce by a half the processing time, at least from what I saw locally. So if my account, I guess if I ask for a service quota, they might increase for me to do this test. But my guess is that as soon as you get an extra CPU, you reduce the price. But then as you increase memory until you reach the next threshold that increases the CPU again, you're just going to be increasing costs without any benefit. So it's going to depend entirely on the algorithm, on the problem, how long it makes sense to wait for this thing to run, because the larger the file, the longer it's going to take. So you cannot avoid that, the fact that this is always going to cost more to process compared to this, because it's double the data. So you're going to have to pay for the process, but if you can wait long enough to do a batch, it just might be more performant. In my case, it is at around this size memory, but it's super tricky to get to the right number. And I think this tool makes it a lot faster and a lot easier to find out where are these thresholds, where are these memory points which are ideal. So it takes a lot of error and trial.
Right. I wonder, how does this work, all this knowledge? How can we compare between different services? For example, if we are using Spark or Glue or EMR in terms of processing like a big payload with multiple computers, I wonder what will be at the end cheaper if and performance in terms of, because I think would be interesting to understand what are the thresholds that help us to know if we should go to Glue or EMR instead of Lambda, for example, because those kind of services are like built for to compute like with satellite images, for example. So, and on the other hand, I'm thinking, how can we compare ECS with Fargate to process, I mean, or with even an ECS that we can start and stop to process something. I think this tool looks amazing, but bring me to some new questions about in terms of cost and at the time to choose for a real customer, we should go for an EC2 or an ECS with Fargate that could be like a kind of serverless and will change on demand without the scaling. Or if we are working with a pretty big payload, maybe we will need to choose a Glue, for example.
And those tools, I think they have enough optimizations under the hood that they make themselves cheaper because they're specialized for data processing. I think this kind of tool is more suitable for things that are custom algorithms, just custom things that you have a very specific program or algorithm, and there's no tailor-made solution for it. So you can optimize the best you can using Lambda. But yeah, after a certain point, if you're solving a problem that's well understood, like a data transformation under big data, then I don't think Lambda would be the best way. I think, like you mentioned, Spark and other big data solutions, those are probably better to work with and cheaper, just because they're tailor-made for that specific problem. This is a more generic solution that might work in most cases, but
looks like a good starting point, right? To understand maybe what to choose next, maybe.
Yeah. I think there are many use cases, and it might be, for example, if you have data in Dynamo and you have big JSONs and you're pulling them in, it might be useful to see, for example, something is taking too long, or some lambdas are being very costly because they're running for too much time. It's probably because they have not enough memory to work with. So you increase the memory and they start to work, because it's different problems. Like one problem is computing for real-time applications that the user is interacting. And another use case is data transformation, ETL pipelines, which don't need a user input and output, but it's big data transformation. And there are different tools, I think, for different jobs.
Yeah. Thank you, Marcelo. Awesome.
Thanks a lot for the questions. All right. Thank you for joining.